Here I am in Python for our column. So I've just got our initial variables set, our initial libraries imported, and also just a setup. So we've got a condenser, 2 stages, feed, 2 more stages, and then the reboiler. How this will be set up is index 0 is our condenser. We go 1, 2, 3, 4, 5, 6 down the column there. So just to start initializing some variables, we have our feed flow at 1 mole per second, our Z, which is the mole fraction of the more volatile component at 0.5. Alpha is our relative volatility, and later we'll be doing something with x times alpha over 1 minus x plus x times alpha. And that'll be how we determine our phi value here. That's for later. When we're actually plugging in, or when we're actually creating our function. Next up, we've got m naught equals 1.2. That's the number of moles in a tray before it starts flowing over. We have a reflux ratio of 1, a distillate flow rate of 0.6 moles per second, and our bottom flow rate is going to be our feed minus our distillate. And then we also have Q equals 0.9. That's the mole fraction of the feed flow in the liquid phase. Now I'm going to make this tab a little bigger here. Yeah, so now we can go ahead with our liquid flow in the top section. That's going to be everything, all of our reflux. Of course, it's our reflux ratio times our distillate. And then we've got LV, which is going to be equal to LP plus everything coming in from the feed. We've got our vapor flow in the top section. So for that, we're going to look at everything going into the condenser. Comes out, we have no accumulation. So VT equals LP plus our distillate. And then VB equals VT minus everything added by our flow. The reason this is plus and this is minus is because when the flow comes in on the liquid flows down, adds to the bottoms. When the feed flows in the vapor phase, it goes up, adds to the top. All right. So now I'm going to use our Francis-Weir. So I do need my Francis-Weir constant, so that'll be 12. What this says is that our liquid flow equals FW times M minus M naught to the 1.5. So now I'm just doing some algebra. So that divide by FW, take the do the 2/3 root, and we just add M naught to both sides. And then, of course, rearrange so that Python knows what's going on. We have this equation. And then we can just change that for MB and LB. And then the last thing I'll be doing before we move on to our function is just setting up our initial values. So for x, we will just do z. So that's saying the mole fraction of the feed is the mole fraction everywhere. Of course, this is not true, but just for initial variables, we'll be setting it like that. And then for moles in each tray, we'll be doing 10 times the amount 10 times the holdup in the rectifying and stripping section. So I'll just be 10 times MT, and then MT by 2, MT by 3, and then 10, MB times 3, and then 10 times MB. And F. Alright, I believe that could be all. So now we'll move on to defining our right-hand side. So we have time and a vector. That vector is going to be split into x and m. So we have an np dot split 2. And then here's our, I tried to copy and paste it, but I copied something else. We have our relative volatility. That's 1 minus x times, plus x times alpha. Now I want to create a vector for a vapor flow. So np zeros like m, and then also for a liquid flow. np zeros like m. So what we can do is we'll just take these, take this guy. And so this way it'll be able to change with time. We'll make that L0, and then both of those should be the same. Our L1 through -1 is going to be based off of our Francis Weir. So FW times M1 through -1 minus M naught, 1.5 power. And then our -1 is going to be based off of our controller, of KC was 1.5, and then our controlled bottom's flow rate is going to be equal to B plus 1.5 times M of -1 minus 10 times M naught. And then L of -1 is going to be equal to our control B if that is greater than 0. Else, we'll just make it 0. Right. And then, yeah, I think now we can move on to our change in moles over time. So first we will initialize a vector, and then we have dn of 1 to -1. This is going to be equal to all of the vapor flowing in. So that will be 2 to the n, because those higher numbers are actually below, minus the vapor flowing up, so 1 to -1, plus the liquid flowing in, minus the liquid flowing out. And then we have for PM3, that's our feed tray, we have plus equals F. dm of 0, we have the vapor flowing in, minus our liquid out, minus our distillate. Now, this is always going to be 0, just because we have our perfect condensation. There's no accumulation or anything. But of course, if that were to change, that would be more relevant. Then we have dm of -1. So this is in our reboiler. So there's no vapor flowing in. There is vapor flowing out. And we also add your liquid flowing in. And we subtract the liquid flowing out. Alright. Now we have to work with dx. But we don't actually have a direct way to get the mole fraction of the more volatile liquid. So what we can actually do instead is use dmx. And I will first initialize this and then explain. So dmx is going to be our product. Right? It's going to be a d of m times x. So this will be dm times x plus dx times m. Doing some algebra. Oh, back. Yeah, ran to the door, knocked out my webcam, which I didn't realize meant that when I plugged it in, it would start picking up sound again. So the sound was all messed up, so I had to reset. I finished the whole thing, but here I am back again. So we have this DMX, right? That molar flow of just the more volatile component, and then just rearranging that product rule, we get our dx. And then what I'm going to do is just copy and paste that. And then each of these flows, we are going to multiply by the composition. So in the, vapor flow, obviously we multiply by the vapor phase composition. And this is the composition of the more volatile component. Hitting all sorts of buttons. And then our flow feed, we're just going to multiply by z. Our distillate will be multiplied by x naught. And then x negative 1. And then we'll return this as a row concatenation of dx and dm. One thing I did notice earlier, I had equals and then plus. I did go ahead and switch that. I don't know if that makes a difference, but I did switch it. And then also we have our vapor. So I didn't actually initialize this. Or, sorry, I didn't actually put in these values. I just had all zeros. But we just have a row concatenation with 0 in the condenser, and then stage 1, 2 in the feed are our top vapor flow, and then our bottom vapor flow is going to be 4, 5 in the reboiler. Right, so that should be all, and it should just be solving IVP from here and graphing. So both np.lin space 0, 500 t end. Oh, sorry. 500 is t end. And then we'll have our result equals solve IVP of right hand side from 0 to t end. A row concatenation of xi and mi. Method equals then output equals true. And then we'll do res.sol for t-plot. Right, and this will be our x's and our m's. So we'll need to split that because we have two different vectors for it to go into. Then we can start reading our figure here. So make subplots. Rows equals 1, columns equals 2. And then for I, xm in enumerate the zip of x's m's. Right, so what this is doing is it's setting an I value, and it corresponds to one column in the x and one column in the m. We can do fig.add scatter, and scatter x equals t plot, y equals x, mode equals lines, name equals an f string of xi, and then row equals 1, column equals 1. And then we copy and paste. And then just write in our figure. Alright, so here we go. We have on this left side all of our mole fractions of that higher volatility component. So we see they all start at 0.5, which of course we knew was not going to be the steady state. And very quickly, our condenser reaches a very high mole fraction of that component, of the more volatile component, and then x1 a little less, and then x2, x3, x4, so on. So these stages actually show that the more volatile component is higher up in the column, which of course makes sense because more of it will be vapor, and vapor rises, the liquid falls. On this other side here, we have our number of moles in each tray. So of course our condenser and our reboiler are 10 times all of the others. Here's M naught, that's our condenser, at a 13.35, it's steady state. And then our M6 actually changes. That one is our reboiler, which we set a controller to here. Right, so that controller does a little bit of work, stabilizes it a little bit. If I just go ahead and remove these two, you can actually see these guys are way down here. We've got our lower trays up at 1.45, and then our higher trays at 1.34-ish, which of course corresponds to the starting point of these two values, right? Because these are just 10 times that. Then there's no really change here at all, other than the one with the controller. So now I'll be moving on to part C,